Hi, in this video I'm going to be walking you through the process of simplifying a radical expression that involves variables, involves x's and y's and z's, and this is a pretty standard problem you might see on the end of course exam. Math people like this because it forces you to actually know rules of exponents and radicals and how to work with things without being able to type things in your calculator, because you can't type an expression like this in. So be prepared for kind of a problem like this, maybe on the ACT or end of course exam coming up here in a month or so. So let's start off by dealing with number 1. I'm going to do problems 1, 3, 5, and 12 off of your homework assignment in these notes. And so that really only leaves you 8 more homework problems to work with. And the big idea is this, okay? I'm going to show you a couple of different ways to look at a problem like number 1. First of all, if we have the square root of 49, x to the 5th power, and I want to simplify it, what it means is that I want to give as much as possible outside of the radical sign, okay? So in other words, if I can simplify the square root of 49, which I can, or if I can simplify the square root of x to the 5th, which I can, I want to write it in that simplest format, okay? So I would suggest doing this perhaps to start off with. See, the square root of 49 x to the 5th is really the same thing as the square root of 49 times the square root of x to the 5th, okay? I know the square root of 49, that's just 7. But the problem is, how do I deal with this x to the 5th? It might be helpful to think of x to the 5th as really, and there's a reason, I'll show you this in just a second. So you remember x squared, square root, sorry, is really, it has a 2 up here, even though it's not written, right? It has a 2. And so what we're looking for is x squareds inside of here that might cancel out, right? The 49 is a perfect square of 7. So if I could write it, say for instance, as x to the 5th, if I could write it like this instead, it's going to help me see what's going on. See, really, I have 5 x's multiplied together. It's 2 x's, 2 x's, and then one oddball remaining x, right, to give me the 5th. And if I look at it that way, see what it becomes is 7 times the square root of x squared times the square root of another x squared times the square root of x, right? I can break those up into separate ones. And then what that means is I have a square root of a square here. And it happens twice, actually. Both of these are a square root of a square, and those end up turning into just plain old x's. So it's 7 times x times another x, and then I have that oddball square root of x on the outside, right? So the simplified form of this would be 7 times x times another x gives me 7x squared. And then I have the square root of x on the inside that's left over. I can't pull it out because it doesn't have a perfect square, right? It's not a perfect square that I can pull out. So the simplified version of this would be 7x squared times the square root of x. Of course, one of the first questions I get is, how is that simpler? And to be perfectly honest with you, I don't know. I don't know how that's simpler. But we're going to need to do that in order to work with numbers and stuff later on. So just get used to the idea, okay? That's really what we're doing. Here's another approach that you might take that some people might like more, and I don't mind this approach at all. It's working with fractional exponents, with rational exponents, right? So if I have the square root of, say, 49 x to the 5th, here's another way to look at it, okay? Maybe I'll show you 3 ways, and then I'll just make this one video, okay? First of all, the 7, it's easy to see. It's the square root of 49, right? So we're going to pull that on this outside. Instead of calling it the square root of 49, we're going to call it the square root of 7. Or, sorry, not the square root of 7, just a plain old 7, right? If I remember this, then, it's the square root of x to the 5th. I might think of this instead of the square root of x to the 5th. Maybe I'll think of this as x to the 5 halves. If you remember rewriting those, radical form in this form, okay? And that might help me figure out what's going on. See, 5 halves is really the same thing as 2 and 1/2, right? If I rewrote that in that form. And if I get a 2 and a 1/2, that really means I have a 2 plus a 1/2, right? And when do I add exponents together? I do it when I multiply things, right? So I might think of this then as x squared times x to the 1/2 power, right? Wouldn't that give me x to the 5 halves? That'd be 2.5. This is 2.5. It's the same thing. So really, don't forget the 7. Really, we have this. If I think about it in fractional exponent form, I have 7. I have x squared, and I have x to the 1/2. That's really what's going on here. Well, the 7x squared then is easy enough. And all I do is, if I have a fractional exponent, 1/2 is really the same thing as a square root. So I put it back in radical form at the end. Okay? There's a second way to think about it. One more way, okay? Because I want you to have a variety of ways to attack this. I really just need your mind to be able to digest this information, to be able to get the correct answer. So let's look at one last way. I still think the 7 is easy. We're still dealing with that, right? Okay, so if the number up here is unwritten, it's really a 2, okay? It's assumed to be a 2, a square root. And so what I do then is I look for pairs. How many times can I pull a square out of this? Okay, because this is a 2, how many times can I pull a square out of this? And if I think about, well, I could get x to the 4th, right, out of this, okay? That means I could pull x squared out of it not only once, but I could pull it out twice. I could pull 2 x squareds out, and that would leave me with the oddball x on the inside. And so I would be left with 7 times an x times the square root of x in that way. An x squared comes out and forms this one. A second x squared comes out and forms this x here. I'm left with the 5th x still on the inside, right? And so that forms 7x squared times the square root of x. Now this example is one that we're going to rely on later whenever we get to cubes and higher powers and stuff like this. So hopefully in doing the problems, eventually this method will make sense, okay? Maybe not so far. So you got 3 different ways. I can either break it down like this, call x to the 5th x squared times x, and then form each individual one, right? Look for squares to cancel out square roots. Or I can do fractional exponents, say, well, that's really x to the 5 halves, and 5 halves is really 2 1/2, so I'm going to have x squared and x 1/2. That's 2 plus 1/2 when I combine those. Or I can think about it as how many pairs of x's can I pull out of this? I can pull out 2 pairs, separate pairs of x's, to form individual x's on the outside because you're canceling out the perfect square. So we'll see what works. Obviously, the only way to really tell is to practice these things, and eventually you're going to figure out a pattern. You're going to go, oh, this isn't too bad at all, right? So that's the goal, and we'll work on that in class.